this is right here, and today we're going to go over the lesson of 3.2 zeros of polynomials. We're going to go over part 1. So right now let's jump into factoring. So what's the definition of a zero? The definition of a zero is the value of x, which f of x equals 0. That's like I just said. So right here, if x were to be negative 3, then this whole parentheses would equal 0. Meaning when it times this 0, times this 0, times this, everything is 0. So that results in f of x equals 0. So negative 3 works. But what I want to focus on here is the irrational and complex imaginary zeros. So why do these irrational zeros and complex imaginary zeros always come in pairs that look something like their opposite? Well, it's because they're conjugates. So if we've done exponential and radicals before last year, so let me show you why it's always in pairs. So to show you, we have to go to factoring. So right now we're going to use a difference of squares. So a squared minus b squared equals parentheses a minus b times parentheses a plus b. So that would, for this example, be 3x minus 4 times 3x plus 4. Let's just sort of memorize them. Just utilize this first. Just don't care about the others. And so this, if you have to factor this, it would be x minus square root of 2, because what is for example, b squared equals 2. What's b? B equals square root of 2. Except but we don't put the plus or minus here in this example because it's a rule that actually, yeah, you can add the plus or minus, because guess what? B plus or minus equals 2. You're still gonna have plus or minus for this one, so it doesn't really matter. So the square root of 2 would be b, and so that would also result in this. So in order to get irrational zeros, they have to come in pairs, in conjugates, or else it can't, because their function most likely doesn't contain radicals in them. In fact, I think it can't. So that means all of this has to come in pairs. Let me give you another example. For example, it works the same way if I were to have x to the 4th minus 3 equals f of x. So what would this be? This would be x squared minus square root of 3 and x squared plus square root of 3. Well, that wouldn't be in complete factor form, but that would give you a pretty basic idea of why you would have all these pairs. This, in fact, is not factor form, but it would give you a pretty good idea why they always come in pairs, because they have to come from a rational number, and because either a difference of 2 cubes, or difference of 2 squares, or some difference of 2 cubes. Because of that, it's going to transform into irrational zeros. So now we've covered rational zeros. What about complex imaginary? So it works the same way. Actually, so there's not much difference. Using the formula, let's just write it. A squared minus, I really love this formula. A plus b times a minus b. And so for this example, if we have f of x equals x squared plus 1, well, you might think, whoa, wait a second. It's plus 1. This is minus, and this is plus. That's different. But we can remember, complex numbers are really complex. So we can change that into negative and into 1. So this would become b, and this would become, this would be b squared, and this would become sorry, this would become a squared. So that would be a squared minus b squared. So that would work, except it would be complex. So right now it's a squared. So let's get a. So a is x plus. What's the square root of -1? I. So now you have the thinking process when you try to get an imaginary root. So it's very hard to comprehend at first because you look at it and you just skip over it because it's plus. But when the problem asks you to include complex imaginary zeros and irrational, you have to think hard and try to find the mistake. Sort of. So x plus I, x minus I.